school was um, to be a co-founder of Wolfram Research. People are seeing my screen, right?
Yes, we are. Mm-hmm.
Okay, good. So Wolfram Research, makers of Mathematica, Wolfram Alpha. My first sort of contribution there was developing the notebook user interface, which has since been lovingly copied by Jupyter Notebooks. But ours was the best in the first. But along the way, I got distracted. So I read this book, Uncle Tungsten by Oliver Sacks, and it's a great book. It's highly recommended. Um, and he talks about visiting a periodic table in a museum in London. And I thought the way that he wrote the sentence about this, I thought he meant a table that was shaped like the periodic table, which just that I thought that was such a brilliant idea. Like, what a great concept for a science museum to have a table, and it's the periodic table. But it turns out I was just confused, or maybe he wrote it confusingly. They don't have a periodic table. It's just on the wall. But I thought, okay, well, I have to build one. Like, this is such an obvious idea. And Googling didn't show up anybody else had ever built one, which seems hard to believe. Um, so I thought, okay, clearly it is my destiny. I need to build this table. And so I did. I happened to do sort of woodworking as a hobby. So I built this table, and and that's what it is. It's a wooden periodic table. It's completely silly. It has no deeper meaning. It's just a joke. And it's a joke that only works in English and whatever. Didn't really think much of it. But I did sort of, for various reasons, build it with compartments underneath each of the little engraved element tiles. And I thought I should put the actual elements in those compartments and have like an element collection. Um, Again, no reason for it. And eBay had recently been invented, so there was a place to go to buy all kinds of weird stuff. And I just started collecting elements, and pretty soon I had thousands of them. Um, and then at one point, Oliver Sacks, who wrote the book that inspired me, came to visit this table because it had gotten some attention. Um, and it was a great honor. It was amazing to meet the person whose confusingly written sentence had sent me off on this crazy side quest of building a periodic table. And we had a great time. And then the Ig Nobel Prize. Stop this. Yeah, it's too loud. Anyway, we won the Ig Nobel Prize, which is a prize, a joke prize for, completely pointless accomplishments, but somehow they're funny, or, whatever. And they're fairly popular, and so this caused more attention. And then the editor of Popular Science magazine, which I recently heard is now actually definitively closed down for good after like 150 years or something. All these magazines, National Geographic has stopped publishing. It's sad.
Wow.
So anyway, I wrote a column for them. They wanted me to write a column about, science or something, which I had never done before. But they saw the periodic table, and they saw I had a website where I had some descriptions of stuff that's in it. And they just called up and said, "Hey, do you want to write a column for us?" I was like, "Sure." I don't know how to do that, but whatever. And so I started doing that. I did it every month, pretty much every month for just about 10 years straight. Um, and I also, in between, wrote a book about the elements because I had so many of them and I've been taking pictures of them. And I felt like I had something to say. And then the iPad came out, and I sort of had a long association with Apple, and we actually had pre-release versions of the iPad, like prototype iPads, a couple months before the public release, so we could develop an app for it, which was really cool. And that app was, an app of my Elements book, and Apple liked it, and they promoted it, and we sold a whole bunch of copies. And um, it was just kind of this continuous slippery slope of like, I just thought it was funny, that the periodic table, that seemed like a funny idea. And now, I'm on stage with Steve Jobs and he's talking about this app, and it wasn't really planned that way, but whatever, it happened. So I kind of stumbled into this role. Like, yes, I have a bachelor's degree in chemistry, and I spent a year at Berkeley, studying to be a professor of chemistry or something, which seemed to be my fate. But what I've ended up doing, it's not science, it's science communication. It's talking to people about science, not actually doing science. And, so partly this talk is to defend that as a valuable thing to do. Um,
You don't have to. We're cool with that.
okay, well, I don't know. My parents were both math professors, like very serious, like they made contributions to the world. So I kind of feel like, I was supposed to be a chemistry professor, and then I dropped out of graduate school. So I have a latent need to justify my life as, you know, anyway, they did actually come to they both came to the Ig Nobel Prize awards ceremony and watched me shaking hands with a real Nobel Prize winner. It's like, that's the closest they're going to get to any sort of academic distinction from their son. Anyway, so here's an example of what I mean by science communication and how you sort of explain how science helps you see the world. So one of the things that I live in the Midwest, and in the Midwest, we use propane for heating if you're out in the country. Like if you're out in the countryside, you don't have a natural gas hookup from the city. I think along the East Coast, people mainly use heating oil and it comes in a truck. People out in the country here, they use propane. I don't know why the difference. But propane has this property that it's a gas, but it's a relatively viscous gas and is heavier than air. So if you have a propane leak in your house, the propane will accumulate in the basement. And you read every year, there's at least one or two newspaper articles about, Farmer Bob came home from vacation and his roof was in his basement and all the walls were out in the cornfield. It's always a cornfield or a soybean field because that's the only thing we grow around here. And the roof is always in the basement and nobody's ever hurt. I mean, occasionally there are injuries or even fatalities, but usually nobody is hurt. And the reason is because the propane has accumulated in the basement. If anybody's home, you smell it. They put in a special chemical. It's very distinctive smell. And you get out before anything happens because you know what that means. But if you're not home, it accumulates. Eventually, it reaches a pilot light or some kind of a source of ignition. And then there's a tremendous explosion and the entire house is decimated. So the question is, how do we understand the fact that propane will literally blow your house into sticks, but at the same time, it will burn slowly and gently in a stove or a furnace or something like that, or a propane plumbing torch? Why is it that this same gas behaves in these two completely different ways? And the explanation, of course, is that in the stove or the sort of controlled flame situation, the rate of the reaction is limited by mixing of the propane with the oxygen from the air around it. The actual reaction between propane and oxygen is very, very fast, but it can't happen fast because the reactants are being metered towards given to each other at a slow rate and being consumed, continuously as they're being brought together. So it never gets a chance to do the fast kind of the reaction. But if you fill up a space and you allow it to mix ahead of time, and then you ignite it, then you get a powerful explosion. And there's a beautiful standard chemical demonstration, which you'll see at Christmas magic shows. If you go to a chemistry magic show at a university, they will do the hydrogen soap bubbles, which start off with pure hydrogen soap bubbles. You blow hydrogen that's lighter than air, the soap bubbles float up. You light it with a candle at the end of a stick or something like that. And it makes a sort of a whoosh, a big flame, a nice little red fireball, beautiful. Then you start mixing in some oxygen in with the hydrogen so that there's a mixture of gases in there. And the flame it gets sharper. And eventually you end up with, it sounds like a shotgun and it knocks the chalk off the boards if you still have chalkboards. And it's a tremendously powerful explosion because when you premix the gases, you get an explosion. When they have to mix as they're reacting, you get a flame. And this is, I think, a beautiful, simple, not difficult to understand or explain principle that helps you understand a lot of things. Like, I don't know, I guess showing my age, during the Iran-Iraq War, there was a lot of talk about these fuel air bombs, the MOABs, the mother of all bombs or something, which are basically just gasoline. And yet they're the most powerful bombs in non-nuclear bombs in the world. And the way they work is there's a small compressed air charge or something which disperses a vapor over a large area and then a second later ignites it. So it creates a big cloud of mixed gas and air and lights that, and that will create a percussion wave so intense that it'll set off landmines in a 100-yard radius. And it's just, it's a tremendously powerful explosion using the same principle. So, I think that's a nice example of how, if you can get somebody to understand that concept of rates of reaction limited by mixing. Sounds very dry, but it's actually, it's a useful general thing to be able to think about how the world works. For some reason it never. Oh, so here's a video of that. That's pure hydrogen, and complained while I was. Okay, you guys. Oh, maybe we have to. No, never mind. The video's too long. We're in a hurry. So in fact, let's even skip this one. Well, this one is fun. This is making salt. You probably heard about salt. You buy it in the store. It makes things taste better. And you probably know that it's sodium chloride. Sodium and chlorine combined. Sodium is a metal that explodes on contact with water. It's great fun to throw into lakes. Chlorine is a deadly poison that was used in World War I as a poison gas. Incredibly nasty stuff. But somehow when you combine them into sodium chloride, you can, and here, this is an example. We have a little bowl of molten sodium, and then I got a little lecture cylinder of chlorine, and we're blowing the chlorine into the sodium. And of course, they react quite aggressively, and you get billowing white clouds of smoke, which is salt. The smoke is salt. So we were salting popcorn here. And then I didn't really take into account that it was also hot, and the net melted, and then the popcorn fell into the molten sodium. And we got this beautiful picture of little balls of flaming molten sodium shooting out in all directions.
And it's hooked up to a cylinder of oxygen gas.
Skip that one. That's a bacon torch. It cuts steel using bacon and oxygen. Okay, fine. We'll watch this video a little bit.
And it's hooked up to a cylinder of oxygen gas. Let me turn the gas on and light it.
Oh yeah, so that's burning prosciutto. This one is meant to illustrate the importance of oxygen as an oxidizer, because I think it's going to cut through here pretty soon. Yeah, there we go. So it's cut through the steel cookie sheet.
I didn't see that.
So this is.
Burger King.
So I couldn't hear that. Was that a question or?
Oh, it's a snide comment.
Available at Burger King.
Yes, very, very, very flame broiled. Right. Well, but the point of it is that that very often it's not the fuel, it's the oxidizer, right? Like, for example, do you know what is the fuel in the Saturn V moon rocket? The thing that took us to the moon. What fuel does it burn? Does anybody know?
I don't know.
Kerosene. It's kerosene. It's basically diesel fuel. It's the same thing that a truck runs on.
Diesel fuel. Oh wow.
But it's kerosene plus liquid oxygen. And it's the liquid oxygen, like this highly concentrated form of oxygen, that will make almost anything, including bacon, burn incredibly hot, right? Like you can melt steel with bacon as long as you've got pure oxygen as your oxidizer. That was just like a fun illustration of that thing. So the question, is there a point, right? Like, is there a point in doing these kind of silly demonstrations, which I did every month for 10 years in a row for that column. And I think the answer is yes, hopefully, otherwise I wasted 10 years of my life. And one of the things I always tried to do in my column was kind of, metaphorically as well as literally spark interest, leave little breadcrumbs that, particularly the younger readers, this magazine was read largely by sort of teenagers, maybe high school age, that they could Google and they could sort of like, if something seemed intriguing, they could follow the trail, and just kind of show that, you know, there's interesting stuff going on in the world. There's ways of seeing things happening in the world and being able to see more behind it than just the surface appearance. And you know, sort of communicating that you know, by demonstrating that science is actually pretty cool. And you know, there's like, if somebody, you know, if you ever see the old De Beers advertising slogan, "A diamond is forever." Well, no, it's not. We burned one up, right? Diamonds are flammable. You can literally burn diamonds. It's not even that hard. It's just expensive. But you know, if you have a diamond engagement ring and it's in a very, very hot fire and your house burns down or whatever, you'll have a puddle of molten gold and no diamond, because the diamond is consumed by fire. So, you know, diamond is forever? No.
No.
You know, no, it's not. Don't believe what the commercials tell you. Gold, on the other hand, is. And so it turns out that there's a lot of precedent for this kind of, you know, telling people about how valuable science is. And in fact, that is the origin of science. So, you know, science didn't just always exist. It was invented by a group of people. Joseph Banks, Humphrey Davy, Michael Faraday are some of the names associated with the invention of the concept of science as a thing that one could do. You know, previously there were natural philosophers, there were alchemists who were actually quite scientific in many ways. But there was no notion of, let's get a government grant and study a problem because we'll get a useful result. And then, you know, society will be better off because we've solved some problem or we've learned something about the world. That didn't exist as a concept. And these people, I think Joseph Banks is maybe the most directly responsible, invented that idea in England in the 1800s, late 17, early 1800s. And they went to the king, because that's who you go to at that time, and said, hey, we've got some ideas and we would like you to give us money and we will think deep thoughts and we will provide benefits to the British Empire. And I think the initial reaction was kind of like, okay, fine, go away. No, like, what are you talking about? Who do you think you are? And so they had a program of trying to educate the public and the nobility. So in this particular picture, one of the people, I think one of there's a boy sitting on the sort of center. That's like Prince somebody or other, you know, some member of the royal family, several, you know, and they would do demonstrations to show like, look, we can understand this phenomenon. We can do this useful thing, basically building up support among the public and the nobility at the time for the idea that, hey, there's something going on here that's worth supporting. And we could be useful to society if you would give us some more money so we could actually do this full time and not, you know, not just be a pursuit that, you know, only independently wealthy British people could do. And it worked. And they eventually founded the Royal Society. And you know, got together they invented the word scientist. Didn't exist before they invented it. We're going to call ourselves scientists. And they got government grants and started doing science. And you know, Humphrey Davy invented the Davy lamp, which was an explosion-proof lamp that would prevent coal mines from exploding when they carried the lights down there, which allowed the mine owners to go deeper, longer, and kill more people when they did eventually explode. But, you know, it was considered a tremendous invention. Like, it was established, you know, that this is actually really valuable, has practical commercial value. And they continued doing chemistry magic shows. Michael Faraday, you may know the Faraday unit of capacitance. So like a pretty serious guy, made very important contributions to science. Every year he did a lecture series for kids to show off, you know, fun chemistry magic tricks, because he knew that their entire existence as a profession depended on the public believing that they were worthwhile to keep around. And this kind of continues to this day. In fact, we're kind of in a in an era right now where it's particularly important, again, because if the public loses confidence in science as a useful thing to do, which I think very much describes the world we're in right now, that's kind of bad from the point of view of wanting to be a scientist, right? If everybody, including the government, thinks that science is kind of pointless or perhaps worse than pointless and evil or something like that, and certainly not useful, and we don't believe anything that these eggheads are saying, that's a really bad place to be. Not just from the point of view of you're getting grant money to support your work, but from the point of view of society actually being able to continue and continue to function. Like we built a very, very complicated place that we live in now. And without a lot of highly skilled, scientists and technicians to keep things going, the place is going to fall apart. So I think that, I think the founders of the field of science would agree that basically science popularization, trying to get the public to understand, well, who are scientists, what do they do, why do they do it, what's a way that you could participate in this process, is kind of existentially important to the existence of science as a profession. Because, frankly, without the grants, without the support of the public and the government indirectly, it just doesn't exist anymore, it goes away. So which is why it's quite common for universities to this day to hold Christmas chemistry magic shows. I don't know if your university does it, but if they don't, they should. And people go, kids go, and they do explosions and they do color changing reactions, and they do all this stuff. And hopefully that leads to eventually some students deciding that science is cool and that they want to participate. Oh, this is my demonstration of a Davy lamp. It's a thing where you can have a candle inside of a wire mesh in an environment with an explosive mixture of gases, and the flame doesn't travel outside the mesh. It's very surprising. Like, that's propane being blown through the mesh. The flame only goes up to the mesh. Wow. Doesn't go closer. Which is very surprising. And Humphrey Davy invented that. It saved countless lives, except then they just used it as an excuse to go deeper and into more explosive environments. Yeah. Fails. Anyway, so yes, it's important to educate the public. I'm going to keep going quickly. So I have a whole second half of this talk, but I think we probably need to skip it because it's already 5:05. So what is the time here?
You could do maybe another 10 minutes.
Okay.
So. Yeah.
Okay. So let me just skip through this. This is my sugar and cotton analogy thing here, which we're going to skip entirely, but we're going to go right to, okay. So here's two chemicals, two kinds of cotton. On the left is cotton, which is made of pure glucose, because cotton is cellulose, and cellulose is glucose molecules linked together in a particular way, which we are not able to digest. Like, mammals can't break the bonds in cellulose to release the sugars. The one on the right is cotton candy, which is sucrose and bonded in a way that we can't break up. So it's very sweet. And let's see, what was the point of that? Sorry, we're skipping ahead here because I want to get to, well, this is my fun example. Okay, so this is 100 pounds of sugar, 170,000 calories, 14,000% of your daily carb. Sitting on top is this little jar, a little dish of neotame, which has an equal amount of sweetness. And in fact, it is so sweet that, let's imagine that you're a person who doesn't like artificial chemicals and you think that this stuff is toxic. Well, suppose it was as toxic as the most toxic known synthetic chemical, which is VX nerve gas. So supposing neotame were, the most toxic thing known, most toxic synthetic chemical known, and you were to take an amount appropriate to sweeten a cup of coffee and then drink the coffee, okay, you would have a pretty high likelihood of surviving. I mean, it's under the LD50 of VX nerve gas. which is one of the reasons why being worried about poisonous synthetic artificial sweeteners, I think it's very low on my list of things to worry about, because they're so intensely sweet that you just don't have to worry about it. You're taking such an incredibly tiny amount that what could it really do to you? And actually between the two, so this is a mixture of high intensity sweeteners here. Half of these are synthetic, half of them are natural plant extracts like stevia or monk fruit extract, whereas sucralose and acesulfame potassium are synthetic chemicals. One question is like, which of these is healthier, right? You see a lot of products saying, oh, all natural, we use stevia, right? No artificial sweeteners. This drives me up the wall, because both acesulfame potassium and sucralose, because they're synthetic, are required to be pretty carefully tested and evaluated before they're approved as food additives. And there's good evidence that they are not toxic, and they have no known harmful effects. Stevia side, nobody knows. It's a natural extract, so it is untested. There's no requirements to test it. Nobody knows if it's harmful or not. There's every reason to think that it should be, because it's produced by a plant for purposes of killing insects, probably. I don't know if anybody knows this exact. I mean, most sort of intensely active chemicals produced by plants are either fungicides or insecticides, because plants engage in chemical warfare as their principal means of defense. So you got to be suspicious about anything that comes from a plant, and it's untested, and who knows? And so there are plenty of examples of, I think, do I have one here? No, okay. So, yeah, what do I have here? I don't have the example here, but glycyrrhizin, which is the very intense flavoring of licorice, black licorice, a natural extract of sassafras roots used to flavor black licorice. People have died from that chemical, because if you eat something like 100 grams of black licorice a day, which is a crazy amount to eat, but some people have done that over a period of many months, the toxic effects of the natural flavoring in it will actually build up, and it's a chronic liver toxin. So it's natural, but it's not healthy stuff. As opposed to, let's say, saccharin. Saccharin was banned for a while, but they figured out, there have been some indications that maybe it causes cancer, bladder cancer in particular, but they eventually figured out why. Turns out it's a thing that can't possibly happen in humans. And it's been unbanned. Saccharin is now legal again. It's even legal in California. It doesn't even have the California warning on it that almost everything does. And it's clearly, far safer as a synthetic. Like, if there's one sweetener is safe, it's saccharin, because it's been through the ringer. There are still some amusing regulatory vestiges. So cyclamate, right? So saccharin and cyclamate are quite related. Cyclamate is still banned in the US, but is legal in Europe. Whereas saccharin is legal in the US, but banned in Europe. They're like mutually, our sweet and lows are mutually illegal between the Europe and US. But eventually they'll get that sorted out. And the real scandal actually with sweet and low, what I consider the real scandal here is that, see how it says 0 calorie? It's like in all caps, 0 calorie sweetener. This is a lie. There's actually, this packet is 94% glucose sugar, pure sugar. But and 6% saccharin, which is where almost all the sweetness comes from. The sugar is 4 calories. There's 4 calories worth of sugar in this thing. And the FDA regulations allow you to round to the nearest 5 calories. And if it's less than 5, you're allowed to round down. Right? So, I'm diabetic. And as far as I'm concerned, the presence of the natural sweetener sugar, which is, dangerous to me, is scandalous, right? Like, I want the pure artificial, the synthetic saccharin. I don't want this natural stuff. It's bad for me. I need to avoid it. And here you are, if you have to, it's like nutritive dextrose. What is that? That's glucose. right? That's a synonym for glucose that people don't recognize. And anyway, you know, what I'm trying to make the point here is that there's a great deal of harm in the world, or at least a little bit of harm in the world, even in this simple area, caused by people having really screwed up attitudes about chemicals, right? Synthetic is bad. Natural is good. So I have an even more clear-cut example. Oh, there's my glyciners. Right. Okay. So here we've got cocaine, right? It's coca leaf. You can go down to South America and just, you know, buy tea or whatever is perfectly legal. People chew it. No harm to anybody. It's kind of like caffeine, you know, it's coca leaf. You make tea out of it. Cocaine used to be very wide, still is used in medical settings as a topical anesthetic. It's great stuff for toothaches. You used to be able to buy it, the local pharmacy. It is a natural product, right? It's a plant extract. But you know, if you cook it into crack, so this is a video of taking powder cocaine and turning it into crack cocaine, otherwise known as freebase cocaine, you get stuff which is, it's kind of bad.
That's what they call cut when it's shaky on the bottom.
And we won't watch the whole video, but it involved fire. This is how it's done. So you get stuff which is, I mean, crack cocaine is really bad. You know, it's caused a tremendous amount of harm in the world. But the question is, what question do you want to ask about a chemical to determine whether it's harmful? So here's two things next to each other. The one on the left is crack cocaine. The one on the right is heroin. Heroin is a synthetic opioid derivative, right? It's a synthetic chemical, man-made chemical. Both of these chemicals have caused a tremendous amount of harm in the world. Both of them have a huge potential for abuse. Both of them have destroyed countless lives. But if you're going to talk about the relative merits of these two chemicals, the fact that one is natural and one is synthetic, I think is very, very low on the list of things that you should worry about. It's really not the right question to ask.
Yeah.
And yet, in many cases, when people are talking about, is a chemical safe, you know, some food additive safe, the very first question is it natural or is it synthetic?
Right.
It's like the first question. And there isn't even a second question. It's just, if it's natural, oh, it's great, put it in, eat all you want, it's good for you. If it's synthetic, well, we better avoid it, you know? So let's all become, you know, crack addicts instead of heroin addicts because it's all natural, you know? I mean, it sounds ridiculous in this context, but it's equally ridiculous anytime. You know, anytime you have somebody making an argument, you ought to not eat that because it's synthetic, or that's good for you because it's natural. As soon as you hear that argument, you have learned nothing about whether something is good or bad.
Yeah.
And that's, yeah, so that's my little polemic there. Another amusing fact, so I told you about VX nerve agents, the most toxic substance, the most toxic synthetic substance that's ever been created. It's number 4, and a pretty distant 4 on most toxic substances known. And this list is, you get different lists if you look in different places. It's a little bit hard to measure just exactly how toxic is something where, you know, a nanogram of it will kill you. But, you know, it's pretty well all of the most toxic things in the world are natural products. You know, the botulinum toxin, well known, incredibly poisonous. This metatoxin is a thing that accumulates in some kind of sea snails. The poison dart frog gets its poison from some kind of, I think, algae or something. I don't know. Anyway, being natural is dangerous. The world is out to kill you. Plants are trying to kill you because they don't want to be eaten. You know, the natural world is a dangerous place. Maybe I'm exaggerating a little bit, you know, but
We get the point.
but I mean, my main point is that if you're talking to somebody and their argument about whether you should or shouldn't eat something is whether it's natural or synthetic, stop listening to that person because they don't know what they're talking about. That's my main hill I'll die on. So one of the problems with asking the wrong questions is that you're not asking the right questions. So this is there's a study that I read several years ago where they did a DNA fingerprinting on herbal supplements. So they just went around and bought a whole bunch of, popular brands of herbal supplements and took the, the little crumbled leaves and things that were in there and did DNA analysis on them to find out what plant did this come from. And a third of them had none of any of the listed ingredients. Right? None of any of the listed ingredients showed up in the DNA analysis.
It's a scam.
So, they did exactly what I did to take this picture, which is I went out to my backyard and found some old leaves and crumbled them up and put them in a pill. Right?
So
And that's what happens when you don't ask the right questions. Like, do you have any reason to trust this company that's selling you herbal supplements and giving you all this story about how incredibly healthy they are? Well, maybe they're just weeds. And how would you know? Right. So
Yep.
maybe we should end there. I think that's actually pretty much the end of my
That's a
talk
great,
anyway.
that's a great takeaway. Yes, thank you. And we're going to entertain questions, but let's give you. Huh? You could, do you want to do this now?
Yeah, sure.
Yeah.
But can you hear me?
I can hear that. Yes, I couldn't hear any of the applause. Zoom has really good background noise canceling, but I think I could hear you.
You're hearing?
So I actually have a fairly serious question, and that is about marijuana and its use today versus, and the quality and quantity or the intensity of the THC in today's marijuana versus 1960s and 70s marijuana. You have an opinion or a thought about that?
Well, I don't know. I mean, it was legalized in Illinois a few years ago. I know some people who probably smoke too much of it, but I don't know. I don't really have any experience. I do know I have an amusing story, which is in my molecules book, which was written at a time when it was not yet legal in Illinois, but it was legal in Colorado. My photographer, Nick Mann, that I worked with for many years, happened to be traveling to Colorado, and I asked him to bring me back a nice marijuana bud because I wanted to put it in the chapter on, it's like this chapter on painkillers and other sorts of like psychoactive chemicals. And we took this absolutely gorgeous picture of a beautiful green marijuana bud, and it had like, you could see the crystalline THC all over it. It was just gorgeous as a photograph, and we put it in full page in the book, covering the whole page. And Scholastic came back and said, we can't tell you what to put in your book because we're not that kind of company. However, if you have a full page marijuana bud, we're not going to put it in our grade school they have these book fairs that go around to schools every year, and they sell books, and they sold a lot of my Elements book to through those school book fairs. And so we said, okay, fine, we'll make it smaller. And so the crack rock and the heroin rock and the marijuana bud are very small, and we talk about them in a sober way. But I'm sorry, unfortunately, beyond that, I don't have any knowledge of the relative. I mean, I've heard the same thing what you're saying, right? That it's a lot more potent now than it used to be, but I don't really, other than what I've just, heard, I don't know anything about it.
Do you have like some evidence for the comparison?
No, I don't have the evidence for the bears, and I just am just reading in like the Wall Street Journal where people are starting to have psychotic instances from just taking what would be they thought was a normal dose of marijuana, but it turned out to be 10 or 20 times what they were expecting.
I mean, I think it stands to reason. I mean, now that the stuff is legalized in so many places, there's people, much more competent people working more diligently and out in the open on increasing the potency. So I would be surprised if that was not the case.
Right.
And you read about all these like different strands and I don't know. I mean, I like I say, I'd be surprised if that weren't the case, because that would mean that they're wasting their time, because they're clearly working on trying to do that.
You want to come up and do our?
Well,
Yeah, closer
Well,
to.
you talk about the gift he's giving.
So, a question? Go
So
ahead.
I just had a comment I wanted to make.
Mhm.
Can I come closer? Or can I hear?
Can you hear?
Almost. Maybe if he was a bit closer, I could hear better.
So I just wanted to say that your books are what inspired me to
Wow.
want to go into chemistry. I read them as a kid and I read them over and over and over again. And it's just it's seeing you and here, this was like really cool for me to actually come and meet you or talk to you.
Cool. Well, thank you much. I remember the first time that so thank you for not saying the first person who basically told me that story when I was in China and I was giving a talk at a Chinese university, and one of the full-grown college students got up and said, when I was a kid, I read your book. And at first I was like, wait a minute, what? And then I realized, oh my God, I am that old. My book is that old. He really could have been like 10 or 12 years old when he read my book. It was just a bit of a shock. You realize like you're not that young anymore. And it's been that long. But it is tremendously, I mean, thank you for saying that, because it is very satisfying and gratifying to hear that from people.
So one of the things that we talked about was giving 3 books to 3 students. The element, reactions, and molecules, I think. And so we
This is the gift
wanted
he's giving to us.
right, so
Thank
we
you so
give
much.
it
Yeah,
to.
I would just need to know like where to send them and whether I should autograph them
Right.
to a particular name. If you can like
Right.
send me.
Come up and talk about it, what we discussed, yeah.
So anyway, so there's gonna be 3 books.
Mhm.
And Dr. Murray is, Dr. Murray's gonna choose one person who's been actively involved in the seminar process this semester to get one of the books. And then we thought, how can we sort of give opportunity for somebody else to get a book, other books? So the first opportunity is today, and it's a very simple thing. Just look under your chair, and if you see a note that says you've got it, that you have the book. Well, there. Hey, come on up, come on up. Yeah, yeah. So very lucky. Come on up. I want Dr. Ray to see you.
Yes.
Yeah. So this is Andy Yang. Had won your one of the.
Oh, congratulations.
Yeah, he's going on to grad school. Have you figured out where yet?
Haven't heard anything yet.
Haven't heard anything yet. He's applying to grad schools and he's gonna be a fine grad student. So thank you so much for your gift, and we'll figure out another way to get the 3rd gift into.
And the next gift goes to Ian. Come on up, Ian.
So
Tell us some about yourself.
Now,
Tell us
why
about
did you
yourself.
select him?
Because he is one of the most active questioners in the
Yes.
class. Yes.
Indeed.
So tell him something about yourself.
Yeah, I'm a junior in chemistry major, planning on going to graduate school in the future once I, get all plans sorted out and figure out where to go and such, but love chemistry and I'm excited to get the book, I guess.
So, yeah, so we have 3 choices.
Right, so the 3rd and last choice, we'll have a system over the next couple of weeks to select the next.
Yes.
Okay.
Yes,
Whatever the system is, you're gonna have to be here to participate in.
that's right. That's right. Gotta be in class.
Yeah.
So reactions, the elements,
And
and
molecules.
molecules. And you could pass around the reactions. It's really beautifully illustrated. And we want to thank you very much
Yes.
Well,
for
so at some point you're going to send me an email with like names I should.
with names. Yes,
It'll be a
yes,
couple weeks, but we'll send you an email.
yes, yes.
Okay, cool.
All
Thank you
right.
so much.
Thank you. I had one comment too, is I was really interested and glad actually that you went all the way back to those Faraday lectures as your sort of the beginning of science communication.
Well, I
Because
think that
historical
think that
setting is
he-
really important.
Yeah, I mean, I think that Faraday's, recognition of the importance of that
Yeah,
was,
uh-huh,
was very inspirational. I mean, he invented Christmas chemistry magic shows,
right,
right?
right,
And even though he was a very serious, scientist who did, foundational work in electrical theory and electric motors, and got the capacitance unit named after him and all that, he also put a lot of time and effort into just evangelizing science to the
yes,
public and doing
right,
these lectures. And this book, The Chemical History of a Candle, his most famous lecture series, which was turned into a book. It's in print today, and it's considered one of the great classics of science popularization.
What's the
And
name of the book?
The Chemical History of a Candle.
Okay, okay,
And it's based on a series of 6 lectures that he gave, and I think it was 1863 or 4, something like that.
all right.
And one of my ambitions in life is to rewrite it, because the lectures apparently were brilliant. The book is terrible.
Okay.
I mean, it's very badly written, I think. It's like very static, and there's a history of it. It was written by somebody who didn't like for science to be fun. He thought it had to be serious and sober, whereas I'm pretty sure the lectures. Anyway, I want to rewrite that book and restore what I think would have been Faraday's real, flavor of fun and joking and, interacting with the audience someday.
All right, thank you so very much.
Yes, thank you.
Okay.
Again.
Okay, and thanks for everyone for listening.
So I'll stay in touch with you. Thanks.
Okay, let's see.
Okay.
How do I
All right.
I think I'm the presenter, so if I leave, it'll shut this down, all right?
Yeah, I think so.
Bye.
Bye-bye.